Now I'm sharing the screen. Parece bien.
Yeah, after rebooting it.
Okay.
Yeah.
Perfect. Now you have to show the presentation and share the. So you have a mute microphone, closed camera, and speakers sound. Great. Take that. No, up. Have a problem quickly. Great. Continue share.
So is it possible sometimes, there's a, you get a different screen?
You have, no,
not possible.
not possible. With not possible because it's from connection. It's possible when I connect to the directly projector.
Make sure that this is.
It's the only screen because the other screen, not the screen, is a shared presentation.
Okay, I think we're all set.
Yeah.
Do I need to make my no microphone?
Yeah, this is the microphone.
That's why the microphone of the computer should be shut down.
Shut down.
Yes.
Okay.
Yes. You like it? Yeah.
Works. Can you hear me? Is that okay? Can you hear me? Okay, good.
And the last thing is that we have the letter to the rights of using your image.
Sure. Yeah. Okay.
And for this, I will also need a copy of your ID, but we can do that later.
Like
Later.
passport and
Yeah.
or a California ID.
Whatever you want. It's just going to be in a repository, so we can. I will do it right away.
Hello.
you need a pointer. This is the pointer.
This is,
You have one touch in orange. Mute. Again, it's okay.
okay, I'll mute for now.
But not
forget that.
Turn on the
Okay.
And you have to change with these controls, you have to connect this. No have the interface. No have interface.
Now where do I stand, there or here? Where do I stand?
Would you like it?
No, but where do normally people stand? On the top or do they stand?
All the people have to here, and the computer here all the time, but if you prefer stand, no problem, but you have to change. Done. Thank you. You have to change it here and
Hola, Shri. Hola,
Luis,
how are you?
I'm fine. Nice
It's open.
How are the Mexicans treating you?
Yes.
I don't know if it's open.
No, it's on. I've turned. Yeah, but
No, it's closed.
no, it's. Yeah. Hi, Luis. Can you hear me?
Yes,
Oh, okay.
how are the Mexicans treating you?
Yes.
First time for you in Mexico?
Yes, essentially, other than 3 hours in Ensenada on a cruise ship.
Well, enjoy the local food.
Yes, and the pyramids yesterday.
Ah, you were there for the equinox?
No, just that's a good idea though.
Okay.
I just, no? Oh, okay. Okay. Yeah, it's just easier.
You have to show presentation, no problem.
No, I'll then be up there and just.
Okay, that's okay.
Uno, dos.
Yeah, yeah. You have to reboot the computer again. Yeah, yeah. You have to reboot the computer again. Yeah, yeah. You have to reboot the computer again. Yeah, yeah. You have to reboot the computer again. Long time, he said.
Hello. So welcome everyone. As you know, we have the visit this week of people from Caltech and from University of California, in particular of Santa Cruz. They're going to be giving us some lectures, and we have different activities with them. The idea is to plan possible collaborations and possible plans for the future or between California and Mexico, the astrophysical Mexican community. So we have here Sri Kulkarni, we have Enrico Ramirez Ruiz, that you know him very well. We have Ryan Foley from University of California, and we have 3 postdocs here. So I invite you to attend the lectures and to participate in all the meetings that we have with them. We want to thank you for coming to Mexico. And I'm going to give the mic to Aníbal so that he can properly introduce Sri, who will giving the colloquium today. So please, Aníbal, go ahead.
Okay, thank you. It's my pleasure to welcome you all to today's talk. We are honored to have with us Professor Kulkarni, a distinguished professor in several fields of astronomy. He is a professor of astronomy and planetary science at the California Institute of Technology, Caltech, and was the director of the Caltech Optical Observatory, overseeing the Palomar and Keck, among other telescopes. He did his undergraduate studies at the Indian Institute of Technology and a PhD in radioastronomy at UC Berkeley. He joined Caltech in 1985 and has been there ever since. He also got the honorary doctorate from the Radboud University in Nijmegen, the Netherlands. Some highlights of his career include the discovery of the first millisecond pulsar, the first brown dwarf, identifying the soft gamma ray repeaters as galactic objects, and the demonstration that gamma ray bursts are of cosmological origin, and showing that some of the FRBs come from the magnetars. He has advised several PhD students and more than 50 postdoctoral fellows. And today, Professor Kulkarni will be presenting the talk, The Zwicky Transient Facility, Concepts to Results, where we will have the opportunity to gain insight into this field. So please join me in welcoming Professor Kulkarni.
Okay. So, can you hear me okay? Back? Okay, good. So the talk is not so much on the science ZTF has done. That would be a very long talk, and because it's done different kinds of science. It's really, actually there's a very target audience I have in mind, and sorry. Why it's making so much noise. Okay, let's say you're young and you're ambitious and you want to do things. Okay. If you're young and not ambitious, not interesting to you. If you're old and not ambitious, not interesting. The word is ambitious, okay? And what does it take to do a project of this sort? Because you hear of large projects, like LSST, it's like $1 billion project. It does time domain, it does exquisite photometry, exquisite deep imaging. That's a flagship project, like JWST. Those are different things altogether. Okay, so these are sort of PI-led projects where if you're fortunate, if you're lucky, and you can actually take your idea and build it, then how do you go about it? And the reason I'm giving this talk is, in my life, I've changed fields maybe about every 5 or 8 years, and I've done projects at the level, initially at the level of about $500,000, and then later at a few million, and this has been the largest one. And the run-out cost of ZTF is about $30 million spread over 10 years, okay? And the other thing I want to make a point is, everyone thinks this is the decade of time domain astronomy. Suddenly it's become very popular. I remember that in 2007, when I'd already started planning for PTF, I gave a talk at the Institute for Advanced Studies in Princeton and showing some ideas, and then Scott Tremaine said, well, this looks like a lot of butterfly collecting. So in those days, looking at different supernovae or explosions or this, yeah, and I said, yeah, and in fact, I'm very proud that it is butterfly collecting, because all of science starts with butterfly collecting. If you don't understand that, you're not an astronomer at all. Okay, that's a starting point. So now in the US, Astro 2020 has declared we are officially in the decade of time domain astronomy, and now everyone and their brother and their dog and cat wants to do time domain astronomy, as you know. And there have been many time domain astronomy projects. I won't name them. Now, for some of the young people who don't know me, I'm slightly, let's say, an unconventional speaker, and the optical depth between my brain and tongue is exactly 0. Okay. So I won't name them because if you look at the success of these various projects, you'll find it's very divergent. Okay. And so part of this talk is for people who want to do time domain astronomy or doing time domain astronomy. And I will define today precisely what I consider success, and I will give you analysis of why many projects fail. Okay. Now, to tell you a simple bias I have, in my mind, if you're a research scientist, not an educator, a research scientist, I'm very careful. You can be a professor and a researcher, but I'm talking as a researcher. The only metric I care is the number of quality papers you published. I don't care for your ideas. I don't care for your conversation. I simply ask you, a young student meeting, I'll say, or a young researcher, how many papers have you published? Let me look at your list. The list is short. Okay, now let's not worry that you're a Dirac or a de Broglie and that's one paper. No, we're not talking, no, there's no de Broglie or Dirac in this room right now, I know, okay? I was talking about ordinary scientists like me, okay? And I'll see what the number of papers you have, and if it's productive, I'll respect it. If not, I'll say, well, very nice meeting you, and then go on to other things. Okay, so you've got to produce, otherwise you're no one in research. Okay, good. Now we understand this is like, it's in the US, it's very important. Young people want different rubrics and biases. I've given you my bias and rubric exactly at this point. Okay, so why do astronomers do supernovae? I'll use that as a starting point for ZTF. It's one of the different kinds of things ZTF has done, but many times, you have to have a large landscape understanding why you're doing some project at the highest level that you can explain to someone sitting in an airplane who happens to be sitting next to you. They'll say, what research do you do? Okay, then I tell them, I don't tell them I'm studying supernovae. I'll say, well, we are trying to figure out how the periodic table came about. That's the highest level statement of what this project is. Okay? And when the universe began, we know most of the universe was hydrogen, a bit of helium, 9% helium, and a very small amount of lithium. Okay, that is it. But if you look at the composition of Earth today, on which we live, very different. Very, very different, right? In fact, on Earth itself, there's no helium, primordial helium, or any such thing there. So that big thing has just disappeared from Earth. And these various elements are what makes us possible, right? And how did we go from having no chemistry when the universe begins to a life today or to the universe where chemistry is extremely important. Okay? In fact, most of our efforts now are all about chemistry, whether it's in the interstellar medium or biology, it's all about chemistry. Okay, so we know the astronomers of the last century, the biggest progress is we went on understanding, not understanding stars, to knowing that they're essentially fusion reactors, and this fusion reaction and fission reaction can proceed in many diverse ways. So when you look at the periodic table, in this era, you know, for example, you look at iron, now we know that the iron comes from two different kinds of explosive events. It has to be explosive because you have to undergo fusion, and fusion really requires a very high temperature, higher than the sun. The sun can only fuse hydrogen to helium, 10 million Kelvin. But as you go down the periodic table, Z, the nuclear charge is increasing, so the gamma factor is increasing, and so you need to get to high temperatures, which means you have to get to, more extremely warm stars. And then there's some very exotic stars, exotic processes down here, at the very highest Z, which is sort of the state of art work that's happening, especially with the clear link we can now see between the coalescence of two neutron stars and the production of the lanthanides. Okay, so I hope I've given at that highest level. Next time you meet someone in an airplane, don't tell them you're working on novae and supernovae, especially the type 1A. No. People will get very bored, they won't understand. Give them a very big picture, always first. And if they understand, then you give them the smaller picture. So if you want to study this, you have to understand explosions in the sky. Okay? And what we do is actually so much easier to explain than, let's say, a physicist. Imagine if you're working condensed matter, and then you're looking at two-dimensional graphene. I mean, it would be impossible to explain to someone. You can say, it's simple. I take a picture of the sky tonight. I've taken a picture of the sky last night, last year, 10 years ago. I compare with my eyes and see if there's a new object, and that's a supernova. Our subject, we are lucky. We can explain to anyone what we do in a very simple way. Okay, so that's the supernova search is a simple problem, actually. And you can improve it because after a while you get tired by comparing by eye. The human eye is actually quite good at this. You get very tired. So you start image differencing, there are levels of image differencing. Then you can say, can I get to the real noise level? Yeah, but essentially in the end, it's actually a very simple thing. And the universe is rich in supernovae. There's a supernovae every second, somewhere in the universe. So I've been speaking maybe for 5 minutes, 300 supernovae have gone by. Okay, now you have some colleagues, they're in this audience, but I won't tell you who they are. They'll tell you, my new project will find gazillion supernovae every night. Then you should tell them, it's no big deal. Supernovae are very common. Okay, so it's not a question of finding supernovae anymore. 50 years ago, that would have been interesting. You'd have actually sent out a little telegram. I found a supernova. But in the year 2026, you don't do that. Okay. It doesn't matter how many supernovae you find in a night, because most of them you can't study. There's just an abundance of supernovae. It's easy to find them. So we have to now understand why we are studying it in a more detailed way. Okay, and I won't go into that. But I'm exposing a bit of how astronomers tend to think, and this for young people. Whenever someone tells you, oh, we are building this new project, they first of all will tell you how much money it is. So more money is like they are more powerful. And oh, it'll produce a petabyte of data every month or every second. More data, they think it's like even more powerful. You're like, amazing. This is all false. Data is not equal to science. Absolutely not. It is true in astronomy 50 years ago. We were a data-poor science. We are now data-drowning science. So anyone who tells you how many petabytes and this, they really don't understand what they're doing. And they could be very famous people, okay? And never get confused. You can be very famous and still not understand many things. Okay, so it's not, data is not equal to science. Data is the start of science. What do you do with the data distinguishes you from one to the other person. But most importantly, you have to have a motivation of what you want to do. Okay, and that is the big disconnect we have in our field. We have these big machines coming on now, and they all boast about how big they are. Okay, but it's trivial to do those machines now. They may cost $1 billion or 10 billion. Amateurs are now building large arrays of telescopes. They can produce a large amount of data. Okay, so again, young people, don't get confused. You have to have an original idea of what you want to do with the data. Okay, otherwise you'll be counting supernovae like many astronomers do. Okay. Okay, so the start of modern time domain astronomy begins with Professor Fritz Zwicky. It's not that astronomers didn't know about variable sky. In fact, well before that, the Harvard College Observatory was a major force. They had telescopes both in north and south to look for variability. Astronomers, variable stars was a very big thing if you go back about 120 years ago. People had just started realizing famous stars like Lyrae, Cepheid variables, and Novae had just started coming up. Novae stood for Nova Stella, new star. Okay? But Zwicky began a systematic study, not let's take a picture tonight and one maybe a year later, but in a way that you can compute rates. Okay? Pasadena has many famous astronomers. Okay, but in my mind, Zwicky is like the top. He was really amazing physicist, philosopher, observer, absolute genius. So I tend to measure people in Zwicky units. Now, Zwicky is one, of course. Hale is my hero, is one. He went and built telescopes. Not brilliant in Zwicky, but brilliant in other ways, to convince people to give money and have vision, and to do it in your lifetime. Well, that is genius, okay? Many people talk about things, 30 years later, they're still talking. Okay, but Hale built 60-inch, 100-inch, and enabled the 200-inch. 100-inch set the size of the galaxy, size of the universe, all in his lifetime. Okay. So Hale is another. Then there are minor astronomy, astronomers from Pasadena area. They may get some space mission named after them and so on, but mostly I meet Millie Zwickys in my life. Occasionally there's a Senti Zwicky. Okay, so Bard and Zwicky, they're in the early days. Now we are looking at the 30s. Zwicky was the one who, by the way, developed this idea of what we call phase space in the more modern sense. So this is the first phase space in astronomy. In his honor, I simply call it as a Zwicky diagram. Duration of the transient on the x-axis in log scale, 1 day to 1 year. Y-axis is absolute V magnitude. And they found that nova stella, the nova now, more frequent in our galaxy because in the galactic plane, and then occasionally other galaxies, which that concept wasn't still very clear, remember. Okay. But it was getting more clear that these are very bright, million times brighter, so they made a new word, super-nova. But now it's such a regular part of the English language, we no longer hyphenate it, we simply call it a supernova. Okay, so in fact, most of the supernovae that Bard and Zwicky first found were all 1A supernovae, which is not an accident, they are the brightest ones. So in a flux-limited sample, they dominate. Okay, so we see a clear two branches here. Now I'm going to do a psychological test, which I welcome you to all participate. Okay, so the way it works is, I want you to absorb this, and I'll keep quiet for like a few seconds, and then I'll ask you a question. Okay, and the purpose of this test is to determine whether who you are, what sort of, So let's wait. Please absorb this. Okay. Now, what is the big distinction between physics and almost any other subject like biology, astronomy, geology? All these are phenomenological subjects. And we should be very happy because phenomenology is what tells us the way the universe is. Physics is an amazing, forget as a subject, as a philosophy, it's really very interesting. The point of physics is to take these phenomenological data, laws, like Kepler's laws, and try to formulate a physical model based on things we believe are inviolable, like conservation of energy, conservation of momentum. There should be symmetry, because there's nothing so special about us, and so on. Based on these things, to provide a model. So physics is all about reducing all this big stuff into small numbers. So in that sense, physics has been extremely successful. Okay? When you write down F equals minus G M1 M2 over R squared, you write down the entire model for the gravitation, the full evolution of the solar system. You're done, up to a certain precision. So if you're a physicist, you'll immediately look at these two lines here, and you'll say, okay, there's an underlying something here. And you'll try to immediately formulate the two families, and there's something underlying. Okay? Then you're a physicist, which is a good thing, okay? No value comparison. But if you're an explorer, an astronomer, you look and say, my God, there's so much white space here. What do I do to go and discover it? Now you're an explorer, you're an astronomer. Now there's a third category of people. I hope you don't have too many of them in Mexico, who, in my opinion, this whole field, they're wasting their time, and they're called as astroparticle physicists. They'll come up with some nonsense theory about dark matter with this property making this, and dark matter with that property making this, because they have total freedom. Astroparticle physics is a field with zero constraints. It's completely free form. It's like you take drugs and you do physics. Okay, so now you know who you are, okay, and I hope no young person here is ever going to sign up to do astroparticle physics. And after this, maybe I shouldn't have said the drugs, because now maybe you say, maybe that's what I really should be doing. Okay, so let me explain how I got interested in the systematic exploration of the night sky. By nature, I'm an explorer. I love finding new things. And I honestly don't care what subject I work on. I think everything is interesting, if only you can think for 30 seconds. Okay, so the fastest animal in the ocean is a shark. Okay, then, well, this should be of interest if you're an Olympian competing for swimming, right? So you'd say, maybe this shark has very smooth skin because it reduces the viscosity on that. So maybe if I want to win over Olympics, I should wear silk swimsuit. Maybe I should first shave myself to have a more smoother skin. Well, yeah, if you want to win, you have to think about every last percentage. I put on a silk suit. Turns out that's not the right answer. Nature has found this. Sharks have a small amount of roughness, just devised correctly. So they create micro-turbulence, which prevents the creation of macro-turbulence when you have very smooth laminar flow in the back. Isn't this interesting? Amazing? Won't you want to work on this? Yeah, I would. Unfortunately, I'm no Feynman or any such thing, so I have to do with the little gifts I have, which are in astronomy, okay? So you have to be happy with the few things you have in life. Okay, so, but within that, I always say, okay, about every 5 years, I switch fields. My usual idea is find something interesting by thinking deeply about it and by questioning authorities. I love to actually demolish big systems, absolutely. I want to build a project before $1 billion project gets built and do a lot of science. So when they go, they'll be left with the high-hanging fruits, and they need ladders to get there, all that sort of stuff. Nothing more than, it's so much pleasurable to demolish big systems. Okay, but not always possible. Okay, so after I do things in a field and I find I'm writing the same papers, the formula is the same. It looks different. Then I have no patience, no desire. In some ways, I actually respect people who stay in the field for 30, 40 years, their whole lifetime. I mean, they're real dedicated people. They're doing science because they're actually passionate about metallicity of stars in the bulge of galaxy for 40 years. For me, if I'd done a thing like that at 5 years, I'd shoot myself, which is very easy to do in the US, by the way. Okay, so I decided some time ago, I started in radio astronomy, then switched to optical, and I said, okay, I should get into space. So I went to Japan because the US didn't have an X-ray program. And Professor Tanaka invited me before the launch of ASCA, Astro D mission. And the way I switch subject is I just go in, and when I switch subject, I want to teach a class in that. Okay. And the way it works is the first time I teach, bad for students, good for me. You know, like a surgeon, first time is always the bad news. Second time is equal. Third time, very good for students and not for me because I'm not learning anymore. Anyway, so I started teaching a class there on my own. And then I realized there's this whole field of gamma ray astronomy, gamma ray bursts, and which, okay. So I came back from Japan. As I told you, I'm very not suspicious. I have a very clear eye. So I said, this whole field of gamma ray bursts, they're all very focused. You have to understand, when many people get together there, it's very common. You become an echo chamber. So these gamma ray burst guys, they're all talking about the properties of gamma ray bursts. You know, energy, duration. Well, it makes sense. Then they're looking for lags and this. I knew right away, there are some things you don't want to actually waste your time on. You don't want to waste your time, for example, you know, after I found the first millisecond pulsar, one of the things is the questions, do millisecond pulsars emit and have all this complex radio emission the same way as ordinary pulsars? It's a waste of time. This is a very complex problem, and if you're a scientist, the art is not choosing complex problems. The art is choosing solvable problems of importance today, okay? You can always ask difficult questions and feel good. What's before the Big Bang? What's inside a black hole? They're silly questions because what is the new thing you have? Anyway, so from my pulsar experience, I knew that this entire field, they're all on the wrong path. They're all worried about emission details of gamma rays, which is an inherently relativistic non-thermal process, which you don't want to waste your time. And as far as I can tell you, the progress that whole field has made in all these years is very modest. Better than astroparticle physics, which sets the 0 point here. Okay, so I came back and I said, let's go and try to localize this. Anyway, and started a radio program to do what became later called as radio afterglow. Anyway, then it all became a big success. We were able to show gamma ray bursts were extragalactic. We were able to use radio properties to show they underwent superluminal expansion, blah, you know. And so this happened because of Beppo-Sachs, the Italian-Dutch mission, which made the afterglow discovery possible. We are a bit unlucky. If we had found this in a year before, well, it would have been different history. But, you know, life you have to try, but you also need luck. Okay? So 2004, so Beppo-Sachs was finding a gamma ray burst every month. And so, you know, 5 years, 30, well, 60, yeah, about 50 or 60. Now, some of them were not usable. So every burst initially was interesting. And I'm one of these guys, I like writing nature papers because it's not true anymore. Those days it was free. And one thing I really don't like to do is to pay money when I write a paper. Okay. So anyway, we wrote maybe 25 papers in like a few years. It was a nice time. But 2004, I'd gone to a launch of a space mission called Swift X-ray Observatory. Now you're talking of a big mission. And so to Cape Canaveral, it was in November, I think, of 2004. And on the way back after launch, I started thinking, I said, now, with this mission, you're going to get one every 3 days, about 100 bursts, better localized, all of them very well suited to following up. Then I said, this is the time to leave the field, because now everyone and their brother and their dog and cat will be doing GRBs. Okay, so 2005 said bye-bye to the field. I'll now tell you, that's 2005, here's 2026. 21 years later, well, I'll challenge anyone, including especially those on GRBs. I'll tell them, tell me what have you done in the last 20 years? They'll give me a little this and that. It's not much. So you have to choose things carefully. fields go through exponential rise when they're new, then they go through a linear phase. This is the echo chamber phase. They'll keep talking with each other, they'll invent slightly more complicated models, they'll add alpha and a beta, sometimes an epsilon, and at some point actually it starts declining, okay? Okay, so anyway, I said, so you should always, if you're young, don't work in such fields. Not, I mean GRBs, don't work in fields which are rising linearly, because you will never make a name. When you're young, you should be ambitious. You should say, I want to become a Hubble, Hale, or whatever, okay? So you try. You may not succeed. Most of us won't, but you have to try. You should be ambitious, okay? Okay, so one of the nice things about a place like Caltech is called an R1 university. R1 university is a Carnegie designation. It's a university where you have professors who teach, but they also research, or mainly research, but also teach. Whereas many colleges have basically only teachers. And then they have institutions doing only research, which is, I would say that model is, in my opinion, is a flawed model. The US, success of US science and research enterprise has shown, and education, the best way to have research and teaching is through the R1 method, okay? So I was teaching a class, and I decided, I like to make new homework problems. So one of the this was on high energy processes. And the problem I was thinking is you have two neutron stars, they coalesce. This is a complicated problem because it's a many body nuclear interaction problem, and you can get this whole R process. It's very hard to compute the final outcome. You really have to know a lot of nuclear physics. But there's one part we understand this very well. You have these two neutron stars, the neutron, which is largely made of neutrons, a little bit of protons, electrons, and the neutrons in the neutron star are not decaying. Okay, now usually at this point, I would ask first the grad students to raise their hands. Should we do that? Okay, grad students, please raise your hands. Okay, excellent. Well, there are only 3 grad students in this whole lecture hall. I suspect there's not. Okay, I think some are being very clever by not raising their hands. Okay, then I asked the question, why is this neutron in a neutron star not decaying in 10 minutes? If I bring this neutron put in the room, it will decay, okay? I want you to think about that. If you know the answer, please tell me after the lecture. Okay, then I'll talk to you more, because that means you actually thought something about this. Okay, so they coalesce, and there's a small amount of neutrons. Most of it goes into a black hole. So there will be a small amount which will be free, and they will decay in 10 minutes. So this is the simplest source of radioactivity. So it's actually a very nice semi-analytical way to model supernovae. I decided to give this as a homework problem, but then I realized it's actually very interesting when I solved it myself, that it was detectable within a day. I'd not appreciated. With only 10 to the minus 4 solar masses, this is actually detectable. And in astronomy, it's very simple. If you say something, this effect is 10 to the minus 26, it's not detectable, don't talk about this. There are many non-detectable things. You should tell me what is detectable. If it's detectable 5 years from now, it's okay. 50 years from now, no, I'll be dead, you'll be dead, and it's not interesting, okay? So I said, wow, this is interesting. So on the same diagram, I realized that these will start coming here. Then I said, what do I do? How do we go about this? So I realized you need a powerful machine with a large grasp. So that led to, so this first of all led to the idea there's stuff here, supernovae, there's stuff here, and that will happen. And these will be a day, but there's a lot of white space. So at that time, Alex Filippenko is a well-known astronomer at UC Berkeley. He was still doing, I'm not sure, doing the leading edge supernova survey by looking at 10,000 nearby galaxies, maybe not in the same night, but over the whole year, and finding supernovae in nearby galaxies, which led to very definitive rates and very important numerical, hard advances in the field. And he would put out a circular saying we found this thing. So one of the circulars said he's found some object. I said it can't be a supernova, it's too dim, And it was in M85. And immediately I wrote a note to Alex saying, hey Alex, I know you're not interested in this, but I'd like to work on it, send me the details. And I pursued that. And then if you're a place like Caltech, that's a nice thing. You can be a bit lazy, but you have all this observing time. So I was able to pursue that, and in fact, I was able to show that this object was a stellar merger. It's the first one in an extragalactic system. Oh, there's another free nature paper out of that, and it proved that there are stuff in between novae and supernovae. If you find something accidentally like this, that means it's ripe. Okay, so I came with the idea. I was looking at all the supernova searches, and immediately again, because I'm a little suspicious and I'm always skeptical of the system, the supernova surveys, you take pictures, you go to sleep, then you have some undergrad or grad students who will blink or subtract, and then, then a few days later, you have a postdoc who'll get a spectrum. It's what I call a mom and pop operation, okay? Most optical astronomers are very traditional that way. But I'm an engineer at heart. My view is that, why should I do this stuff? I did my thesis at Arecibo. I don't have any affection to going to the observatory, smelling the air, looking at the sky. How romantic it is. No, for me, it's all a machine. I said, okay, I want to build a machine. And this problem is simple. Image, subtract, find, whatever, okay? So the whole idea was to build a machine with no humans in the loop, okay? Because every time you put human in the loop, it slows down. So the best way to do astronomy is not have astronomers in the dome, in any part of the thing. It should be you and the machine, and that's it. Okay, so I said, I want a factory, not a factory, robotic, automated, and no humans in the loop. Okay, so I had this idea, and a friend here, Lars Bilston, who was director of KITP in Santa Barbara, I told him I want to do this, and he said, I'll introduce you to someone. So one day I drove to Santa Barbara, here's the wharf. I had lunch with this gentleman, 12 to 1, it ended at 5. Next day he called me and said, Shri, in what way can I help you? I like this. So young people, again, let me tell you, if you want to be successful in science, it's not enough you have ideas. Ideas are actually quite cheap, okay? They're very common. When you're young, you think, I got this idea. I'm really a Picasso. No, these ideas are very common. The point of being a scientist is to take that idea and complete it and write a paper. If you can do that, otherwise, you're nothing. You're just another person with ideas. Ideas are absolutely cheap, I can tell you that. Okay, so one of the things you have to do many times, less so here, but more in the US, you have to raise money. You can raise money by writing proposals, bringing some friends, increasing your political power, which is the usual way. Or in the US, fortunately, we have this other option, which is you charm your way to rich people and they give you money, which is much better than going to any funding agencies, I can tell you. Much, much better. It's more efficient and just more pleasurable, actually. Anyway, so I've learned rules of how to get money out of rich people. And I want you to remember this. When you want money, ask for advice. When you want advice, ask for money. Okay? So I've been telling Enrico, let's raise some money out of rich people, either in Mexico or in the US, so we can do astronomy. Forget all these funding agencies. They're very slow, they're very orthodox, and by the time it happens, I'll be dead, okay? For me, anything that takes more than a year is death. It's not worth doing. Anyway, so I told him, his name is Wayne Rosing. He was successfully the Vice President for Research for Data General, DEC, Sunworks Systems, and Google, and he retired. Absolutely storied career. I said, give me $1.5 million and a 6-month option period. At the end of that, I will double the money by going around. I said, and I told him why. I said, if this idea is any good, I should get the money. That tells him he's funding it for a good cause. It puts me on notice to actually see if this works. Only if you're a coward, you take the money and say nothing. So I said 6 months, we'll start it. Anyway, I talked to universities, other places, raised the money, and we started. So from concept to first light was 30 months. Extremely important. If you don't have a sense of urgency, you'll always just keep talking. Every day counts. Your working lifetime, let's say, is 40 years. Okay? A year is 300 days, roughly. Let's say 200, maybe you're not working, whatever. All I'm saying is a day is not an insignificant fraction of your active lifetime. Okay, so this led to PTF. Fortunately, Canada France Hawaii had a hand-me-down, the old camera, which we got for $250K. And then I asked the following question, because as you can see, I'm very business-like in this fashion. Now, many of you think, oh, science, I do with my heart, because I'm interested in AGN. Really? It's not like AGN cares much about you. And then if it is, no, I'm really interested in type 2 AGN, then I would say you're a silly person. For sure, at this point. I mean, if someone says I'm very interested in something, I'm already suspicious. Okay, the point is, you want to make a productive scientist. So I said, what is the most productive project in optical astronomy? It's SDSS. So I spent 3 months at the Institute for Advanced Study, because Jordan Bacall used to invite me, and hung around at Bacall and others. So then I studied those papers and I realized, okay, the formula for this is simple. Is the reason SDSS succeeded was because they understood it is not about producing data, it is eyeballs. It's easy to produce data. What you now need to do is get smart eyeballs to look at your data. And there are two ways to shine. One is you analyze the data that you made yourself. I'll call this as self-light, like you're a star, you're emitting. But it turns out the reflected light is usually stronger. Okay, so I said, okay, so that led immediately, I said, okay, when we do this project, we'll get lots of eyeballs, but many times you need money also. So the ideal way is paid eyeballs, or eyeballs which are paid, but that's not enough. So that's why I made the data public. Why? Not because you're a nice person, to get that additional halo effect, okay? So this is a very simple business branding exercise. How do you make Nike shoes popular? That's what this is, okay? Okay, so then the other thing I realized on looking at the other experience, the negative experience of Sloan, was that they had severely underestimated the cost of software, okay? By huge, huge amount, by tens of millions of dollars. So I learned that this is important. And then the other thing is there are many small projects at the $5, $10 million project. You know, people build a spectrograph, they build another time domain survey, and then later you say, what happened to that? Okay, and the reason what happened is they don't have what I call a P2P, photons to papers plan. And I'll end the talk on that, which is you have to have a clarity of why you're doing. Okay, and the other exercise was Tony Tyson had finished the program that he began, which led to the concept of LSST. Okay, and that paper was Tyson. There were 2-3 papers where he explores the sky with the best CCDs then, and then he puts out fast transients. Okay. And I went with a postdoc, investigated all of them. And I found all of them -2 were flares from M dwarfs. The M dwarf was below quiescent flares, okay? So it's an important lesson. When you have a large amount of data, it's not what you're seeking for, it's all the false positives. Okay. Anyway, so this made me realize that this project should not be, I want to find kilonovae, which again, you ask someone, what do you want to do? I want to find kilonovae. Yeah, it's a silly statement. Yeah, you and your brother wants to find kilonovae, so what? But there'll be so many false positives. So you have to say, I want to find the best way to eliminate the false positives for kilonova. That is the right answer when you have data abundance. Now, some of this may appear a little strange to some young people who don't have understanding, but actually these are valuable lessons I'm telling you, okay? Now I've gone much slower, so I have to, anyway, the other thing is, you know, I work with very bright kids because I'm very careful who I work with. And the brighter they are, the more risky projects they get. So a young woman, Mansi, I said, yeah, this is an interesting project. If it fails, it's okay. If you're bright, it doesn't take, as the students, PhD students, they think it's hard to get a PhD. Let me assure you, it's very easy to get a PhD, okay? So if it fails, you can write some 2 or 3 papers. Yeah, next thing you have a PhD. Anyway, so I got her on. And the thing was to get all this very, as I said, software and algorithms was key. So I had all these interesting people. Nick Law had just graduated from Cambridge, working on lucky imaging. And he was a project scientist, a big position for someone who's only 27 years old. Quimby graduated from Texas. He was software lead, worst job because you have to combine all the software. Eran Ofek from Israel for all the robotics. Then later Josh Bloom for the machine learning, which turned out to be very important. Okay, so I'll skip the things. I told you all we do is subtract. And you need machine learning because sometimes the subtraction gives you this by eye, you know it's bad. And we are doing, old style comparing by eye. So Josh came in and instituted. I think this is one of the earliest ML applications in astronomy. So much so, by 3 years later, 2012, Josh then went to Silicon Valley and sold his experience with PTF and founded a company called Wise.io. Machine learning solutions for real-life problems based on a real-life problem. Anyway, then, they sold that company to GE, and he said, then he bought a nice house up in the hills of Berkeley. Then I told him, Josh, like in Indian tradition, the guru, teacher, usually gets a guru dakshina, like a teacher's fee. I was your PhD advisor, I gave you this opportunity. I'd be happy with 10%. He said, I'm not Indian. Okay, that was the end. Anyway, he gave me a nice drink up in the hills, and that's it. Okay, we have follow-up facilities. So I won't go into the science accomplishments because, I don't know, for me it's less interesting personally at this point. PTF, we built, at that time, Pan-STARRS was running at $10 million a year, Air Force money or something. I thought, yeah, we'll get clobbered. I said, let's do for 3 years, because the last thing you want to do is get clobbered. It's best to leave the battlefield before you're struck, okay? You should win, but the next one is, you shouldn't be so obvious. So I said, okay, this Pan-STARRS there. But then I went to a talk by Pan-STARRS scientist. I realized, no, we'll win in this game. Because Pan-STARRS wanted to do everything. Asteroids, catalog of the sky, transients. Whenever you have projects like that, it's easy to take them on. Because when you're hungry for one thing, you can almost kill anyone, okay? And especially the bigger the projects, you can kill them faster. So I was surprised. This project was supposed to run for 3 years and be beaten to death by Pan-STARRS. It became such a success, and there's no comparison at that point. So we extended it to phase 2, understood the importance of robotic spectroscopy. It's easy to find supernovae, okay? And they have a little criticism from my LSST friends. They always talk, we have LSST to find a gadzillion. These are the people who use the word gadzillion, supernovae in a year. I said, so what? What exactly is your plan to use this? I'll tell someone, maybe there are some LSST people here, I'll give you a gadzillion supernovae right now, RA deck, postage stamps, and delta mag. What are you going to do with it? The answer is nothing, because you don't have a P2P plan. You don't have a photons to papers plan, because in order to take that and to make papers, you have to think more than this. And my view is, I've not heard any of even very well accomplished supernova hunters in this game tell me what they're going to do with this data. Okay. I'm not talking of anyone in particular, just to be sure. Okay. So here we tried all sorts of things, mixed cadence. Robotic IFU was very important because we could go from finding a supernova and classifying it in the same hour. So what used to be heroic efforts to find young supernovae is like, I have a party today, I'm not interested in this 2-hour-old supernova. Let's do an experiment on Saturday, okay? Okay, and at this point, a lot of AI came in, really made a big difference, especially for the LIGO problem, which is a needle in the haystack. Okay, so you can see at the end of PTF, not just us, Pan-STARRS, Assassin, astronomers are winning, physicists are losing, there's stuff everywhere, there's new things that are coming on. So this led to ZTF, which is now a large project. It went around the world. I went on the plane, Israel, Sweden, Germany, France, Ireland. If you want to do things, you have to go sell your ideas, your enthusiasm. Okay. There's no way out of that because it's a large project. So it led to ZTF, and we went the opposite way. Here's LSST, 10 square degrees, 6 meter effective telescope. We are 47 degrees, 1 meter effective telescope. Find the brightest things you can follow and study. Then leave the hard ones to the people who are better than you, right? So I've left more faint things to better people. Okay, it was a huge engineering project. I'll just have to, this is not a small amount, and this is the real stuff. Okay, this is the hard stuff. It's not reducing the data and all that. Getting all the engineering right, because you can't screw around. It has to work in the end, and it has to work with not huge delays. Okay, first light, Orion, belt of Orion. That's the size of a camera, it's pretty big. Yeah. And from the lessons learned with Sloan, no data processing by grad students and postdocs, handed to an industrial organization called IPAC. They have a huge heritage in space missions. And we are able to convince Hyacinth Simons Foundations to tell them that it's not the 30,000, 20,000 supernovae candidates we have had in our data. It is what order, how do we prioritize this thing? So the AI ML. So what I call informatics was very important, and they agreed and so funded us for that, and some science. Okay, so here it is. This is so there are many projects. Yeah, okay, here's like the date, supernovae coming up, number of supernovae. And so there are two surveys. One is amongst many other projects, but one is a flux limited sample. At 19th mag, we'll do everyone. Other is a volume limited sample up to about 200 megaparsecs. Okay, now this is the southern sky, which we don't see, galactic plane, obscuration, but you can see, and then it's here we are classifying. If someone tells you I found a supernova candidate, don't be impressed. You should tell me a bit more than that. Okay, these are all classified. Okay. So once in a while, when you have samples like this, weird things happen. Supernova in between galaxy and Enrico's observer, exactly on that line. So we found a supernova with a magnification of 54. Beautiful Einstein ring, multiple things. In fact, if you have excellent data, you can do a geometry of the universe with only one event with as much value as some PAO or whatever project. Okay, this is, so this is the largest classified supernova search. It won't be easily overdone for a long time, I can tell you that. Okay, unless someone takes a 4-meter telescope and say, yeah, what these guys at Caltech did, we will have a real project. Okay, not running around and getting 2 hours here and 2 hours there. That game's over, okay. Okay, so one of the things I had with PTF is this whole thing. I told you about pan-stars. I was worried. They're $10 million, and we are not even anything like that. We are maybe, at that time, $750K a year. But they want to do everything. So the requirement we had for engineering, I said, we'll not do photometry better than 10%. You'd say, why? Why not? Yeah, the moment you start saying, I want to do this, this, and this, you lose focus. You want to win a battle, you should be extremely focused. If you want to win a battle against a more powerful person. Now, some of you are thinking, this guy talks of battles, and why is this? No, it is a battle. This is not it's not like what you're thinking. Yeah, you want to be in this game, and you have people like me, you have to battle. Otherwise, you'll be writing some astroparticle physics papers which are of no value. Okay, so, and I didn't want to be high, because then I thought then people would start doing stellar astronomy and get diverted. Okay, but by this time, my friend Tom Prince said, Shri, transients, you're done, but this big machine, we should do more than that. So we changed the requirement to 2% at this point. And I took you credit for Tom he and his students are revolutionizing ultra-compact binaries. We're getting ready for LISA, which is going to be a wonderful mission. Okay. So the large discovery thing has rare objects. I told you about a supernova. We can find merged white dwarfs, most massive white dwarf. It's clearly a merger. Size is less than the moon. It's rotating rapidly, high magnetic field. Beautiful physics actually at work here. The best one I like, because I guess by nature I'm a little destructive person, is we can actually see planets being engulfed and see that signal. You know, these hot Jupiters will get engulfed by the parent star as it ascends the subgiant branch. And we can see that signature. Okay, it's amazing. This stuff actually works. Okay, another kind of supernova. You know, it's a bit, I'm a little jaded out by that actually. Luminous black hole flares. Okay, but you know, in the end it is this. It's the students, it's the camaraderie, it's the, but that's all good, but it is this. As of last year, 200 papers. The team is now writing a paper every 10 days. We can't do more than this. I think this is maxing out. But there are 5 times more papers for every paper we write. This is the halo effect. Okay, this is why this project is successful. Okay, it's not us guys. We have enabled a large community. And when they write and they put ZTF, then we shine by the reflected light. That's the new way. It's no longer the old ways where Sandage had his photographic plates because it's in a privileged position. It's changed. Okay, so we started off with this simple thing. Now we're getting some very complex. You know, the F bars, the now tidal disruption events. There's a whole wild zoo. Okay, let me skip. I'll skip the one where after this, I started a project called the Ultrasat, which is now going to fly in about 2 years. We'll skip all that. And then I started another project during COVID called UX, which is going to fly in 5 years from now, 4 years from now. I'll skip all that, okay? Because I started with, I said, for me it was very important that I wanted a project where it's an automated discovery of the universe. I was like, why do we need all this processes? I want to really come and say, by the way, you know, I know there's all this thing, artificial intelligence, what to do. You know, I'm not a philosopher. I'm not, in the end, I'm a simple scientist. I'm not God, nothing like that. I really don't care. AI, whatever. I'll use whatever, because my goal is I want to discover the universe in the fastest way in my lifetime, which means total automation and fewer people. So the goal was, can we get to the point where we had machine learning to do the simple pattern recognition, yes, no, to using contextual data and saying, yes. So we observe maybe in a given night, 10 to 30 supernova candidates and 1 million alerts, which filters down to that through all this. And in that, I want to say what is the highest value. So I want the machine to take this action, follow it up with whatever telescopes we have. I come in the morning and it says, dear Shri, this is the most interesting object in my analysis. Okay? That's the goal. Now, some of you might say, well, you're like anti-human and so on. No, I'm totally human at this point. This is the highest level of science to do. Okay? So this is something I was finally achieved, where a very young student working with Adam Miller in Northwestern, that's his Nabil's name, I don't see it here, it's cut off. Anyway, his name is Nabil. It says, to best of our knowledge, SN blah blah, which means the pipeline identified the candidate and had enough machine learning experience to say this is a supernova, that it hands it off for classification to the robotic spectroscopic machine, which observes it, same night, analyzes, comes up with the supernova designation and the redshift. So we go from that, and then it has enough confidence, and we post it directly to the world server for supernova called TNS. No human in the loop. Well, I was extremely happy about this, because now the machine's at the level where I can go and think about it. Okay, so we'll come back to this. Let me end by saying this is a great project for me. This is my backyard. I have a nice orange tree. When you see a tree like this, there are 2 types of people. Okay, there are people who always walk with ladders. They want to put their ladder and go for high-hanging fruits. And there are people like me, I just walk and say, I'll take the low-hanging fruit. This is a fantastic project. And I hope I convince some young people, have ambition, work hard. With some luck, you may succeed. Thank you.
Okay, thank you very much for your talk. So we have time for questions.
Thank you, Dr. Kulkarni. It was a nice talk. A lot of topics, interesting topics. You didn't mention in time domain astronomy recent discoveries in. We only have 3 objects. 1I Oumuamua, 2I Borisov, and 3I Atlas. What about the future findings with the Zwicky Transient Facility? And what do you think about AB Loeb scale? You know the AB Loeb scale of interstellar objects and starship. And are you going to discover a lot of these objects?
Yeah, so it's very interesting. If you look at our accomplishments in the solar system by the ZTF group, it's small. Okay, I think we found a green comet. I don't know what's the importance of that. And we found an asteroid within the orbit of Venus. Sounds cute, but it's not. I mean, there'll be a diffusion of the asteroids and some will go inside, and then it's hard for them to survive. Okay. And it's very simple because we don't have the passion of whoever is in this group to do this. So this goes to show that you can have a large amount of data. If it's got this whole business is what I call as a multiplicative equation. You start with data. That's why I said data is not science. So you start with data, then times passion. That is how much interest. If times knowledge. You may have passion, but if you don't have knowledge, it's and then times hard work. Again, you may have all those two. If you don't do the work, nothing happens. And then maybe plus L for luck. Okay. So if any of those are 0, forget the L. If the other parameters are 0, the answer is 0. This is the great Indian invention. Anything multiplied by 0 is 0. Okay. So this is something my view is that most, even experienced astronomers, directors, people who run all these things, they don't understand. People don't understand this is a very multiplicative game. You want to succeed, you should make sure that your smallest parameter is not close to 0 because it will determine the outcome. So, yeah, I wish we had found this, but honestly, I think it is more rightful that people who care about this found this. No, I don't know this.
Last year in biochemistry journal. 0 is a comet. 1 is a Oort cloud comet, and you go till 5 or 6, it's an interstellar, non-extraterrestrial comet. And 7 to 8, it's sure a starship, alien starship. It's crazy?
No, I haven't given much thought. I haven't spoken to Avi Loeb for a while. It's a joke, okay. No, actually we are friends. Okay, I saw a young person, a graduate student, raise his hand.
Yeah, I have a question. So you mentioned, from what I gathered, that there's a point in any research topic you were researching at which you realized it had become an echo chamber, and so that you realized it was time to move on and switch to another field. So I wanted to know, how do you go on about doing this whilst sort of keeping and being active, as in producing papers? Because I don't know how long it would take, for me at least, to switch from one research topic to another one. So I don't know if you had some other sort of side quests or projects you were working on parallel to the one that was your main one, or if whenever you realized it was the time to make the switch, you would start and delve into this new topic you would now like to investigate.
Okay, there are two separate topics here, okay? And I don't want to confuse the young people, by style of research. The style of research you choose has to be very much who you are, okay? Some people really like to go deep, to dig deep, and I respect that actually. But I'm not a deep well digger, okay? Because the hope here is if you dig deep, you will hit a gush or maybe strike oil or whatever, right? That's one way. The other one is you explore and find new things, okay? So there's no comparison. It is who you are. So if you see someone like me, she's switching subjects, so don't do that. Figure out who you are, okay? And are you a broad, swashbuckling person or dig a well and 30 years later you'll get a gush of oil? Yeah, it is who you are and you choose that. So that's a separate issue. But no matter what it is, let's especially say if you like to be in the same field, my observation, and this applies to many, many people, perhaps most of the people in our field, you should always examine why you're doing that research, okay? Especially the topic is mature. Because many times these fields, they get into doing more or less the same thing. It looks different. It looks different nominally, but it's really the same thing. The modus operandi is exactly the same thing. It's the same old thing. Before you're using, some ground-based near-infrared thing, then you use JWST or maybe WISE. It's the same thing. Then the new thing that happens is because there's a change in the flux, and then you confuse. The new thing is not your ideas here. The new thing is the machine which has given you, instead of millijansky, it's now microjansky. And you think, oh, I'm such a wonderful scientist, I'm writing these nature papers. And all you have to do is really make JWST as the first author, honestly. But we confuse ourselves with the machines, okay? Then you should ask always, what's the new idea here? I would claim most scientists are either, they're very happy, I think, actually. They're contented people. They're happy doing the same thing, okay? Which is fine. It's a way to live life. But if you want to be an ambitious person, you should question authority and yourself all the time. That's all I can tell you.
Thank you very interesting talk. I'm far from being a student, so I passed most of my career, and I usually dedicate, as you say, to a deep research of one particular object. I can spend 10 years to study one object. And what I find is that those theories that are built on the big statistical data, you always find an object that doesn't fit there. And what's your idea? How important is that? It's like in medicine. They develop a vaccine that cures 100,000 people, but 2 or 3 die. Which is the correct answer to this?
Well, as you know, okay, there'll be no simple answer to that. But I have, let's say, first of all, I acknowledge very clearly that there are times when the outlier gives you an absolutely new perspective. Suddenly you realize something, that outlier made it possible for you to see. Okay, and ideally we would like to find those sorts of what I call as outliers which really inform us of something by their sheer extraordinary something, okay? Then there are outliers which are what I call accidents of nature. Okay. There's a little variation here, a little variation there, and as a whole it deviates from the statistical model, which are far more common, okay? But if you set off with a goal, like again I talked to some of I no longer work in the field of time domain astronomy. About 3 years ago, I gave up the PI-ship to younger colleagues who are more ambitious, more interested. Mainly one of the reasons I gave up is I realized I had no new idea in time domain astronomy. It's like zero. I said, okay, it's an unusual situation. So I left the field because I have no new ideas, okay? But once in a while I talk to, now there are many people who are going around. I'm somewhat critical of the LSST crowd, okay? They go around, oh, LSST is like revolutionary, this will do this and do that. Yeah, I know, I have my own ideas where LSST is really unique. My view is that a lot of the things that people are talking about LSST are not unique, okay? So some people are saying, oh, we'll go find outliers. I would say this is a lazy plan. It's a silly plan. It's like being a teenager. Yeah, I want to find, like Aladdin finds a little gold ring and drop and you get a new thing. No. You have to have a plan to say finding an outlier is a guaranteed plan to understanding something. No, I don't see that. So if you want to find outliers, you should actually think deeply about that problem to understand what aspects of nature will you be testing. Okay. And in astronomy, it's a very rich field. You take something like binary stars. There are many parameters, M1, M2, A, eccentricity, when the mass transfer begins, pre-main sequence, AGB, subgiant, AGB, later. So there's a huge diversity built into the problem. And not most outliers are not interesting. They're just slight variation of something. Okay, so searching for outliers as a plan with no deep understanding of the phenomena, as I said, this is not a plan.
Yeah, I didn't mean searching. I mean, if you study each object in depth, you will always find some deviations from those theories that are...
Yeah, and I think you should be the most critical yourself. The moment you find something which is deviant, I always believe you should always publish a paper. If you observe data, you owe it to the people who build the machine and to the funding agencies and all that. You must write. It could be one paragraph paper. It's okay. It should still be there. Okay. But you should say yourself, this looked very different, interesting, but now I realize it's the weird combination. Okay. It's like I met a friend once in Frankfurt airport. Okay. I said, wow, what an amazing thing. Here we are. This guy grew up in India and I grew up here. I hadn't seen him for 20 years and we meet in Frankfurt airport. It's not something that's like some cosmic, amazing thing. You actually sit down and it's a nice little problem to compute. The cross-section, velocity, chance, probability. Okay, so you should be the person evaluating yourself. Instead, I think we have a tendency, understand, especially if you're young, which I forgive most, but the old ones I don't. You're young, you want to say, I found something very interesting because it does that little up instead of doing down. Okay, but if there's no new physics there, you shouldn't. You should be the first one to say, I was very interested, but it turns out it's not so interesting. But the number of people who in time domain who want to use LSST to find weird things is like, this is almost like mainstream plans. And I claim, and I'm telling them all, through this medium and through the YouTube recording, this is silly. Because if you want to do that, why don't you use ZTF? We have 8 years of data. Go find it. That tells me this person has no passion. It's easy to talk of a new project with new possibilities. If you're really passionate, you'd actually look at what's there and formulate your plans.
Okay, any other question? Yeah.
Students?
Yes, students. And now it has to be a woman student. Okay, I'm looking at that group there. They all said the grad students. And I'm not going to hassle you with the free neutron decay, okay? So in return, one of you have to ask a question. I'm looking at you. There, yes. Okay. Okay, girls, step up to the challenge. Yeah, very good.
Well, thank you for the challenge, I think. And my question is, something very important for us as students is, out there, the competition is hard. And developers develop our skills here in Mexico or any other institute is hard. So I don't know if you could tell us something about this topic, the competition and environment of the academic life, that you could say the students could take more easily?
Okay, you say it's hard, okay, because you're in Mexico. I would say, okay, there's another way. Maybe you're from Zimbabwe, right? It's really hard there compared to this. So the question of hard is a degree, and everyone has their own story, okay? There's a Leo Tolstoy book, Anna Katerina. It says, all happy families are alike and all unhappy families are whatever, different. So don't victimize yourself. Nothing. You're here, you have some brains, you have some support from this institute, from your parents. Be bold, be ambitious, work hard. That's it. And see what the next day brings you. You should always be prepared to go and conquer the world. And you should have nothing to stop you. It's good to aim high, but not too high. It's good to jump as high as possible, but not so high that you break your feet, okay? But if you don't jump, you're not going anywhere. So don't go into this little loop that either you're not very good or, no, just be ambitious and use what you have. That's it. Okay, you can look at someone like me. This is not that bright a guy, and suddenly he's doing these things. So yeah, hopefully I can inspire you with a modest amount of brains. You can do big things. The main multiplier is ambition and work. Ambition is the desire, the passion that you want to go and do things. Not just saying, I want to be rich and famous. I don't mean that way. Okay, it's that internal determination. I want to do things. Okay? And hard work is necessary, otherwise, okay? And always question yourself and always question the authorities, okay? I'm almost always sure that most of the world is wrong, which is a good assumption, actually. And especially the system is always, it's never as good as it can be, because when you bring more people, it gets more and more imperfect. It's just how humans are, okay? That's why small groups can do more effectively than a large thing. But for some large things, you need taxpayers' money, so you need more people and so on. You can't do JWST by yourself, but you can do certain things by yourself. Yes?
Hi. First of all, thank you very much for the talk. It was very impressive, all the different points of view you give us. And I have two questions about, some of the topics you mentioned. The first one, you said that you like to be very efficient and to go, photos to papers, let's keep doing papers because this is very, for a scientist, very important. But you also said that when you see something that's like 1 year away, that's it. So when you draw a line, when you get stuck writing a paper and say, okay, this is working, but it's taking more time. I should keep working on this because I know it's going to be very important, or you better say, no, it's not good enough. So I will better just abandon this idea and go to the next one.
Yeah, look, these are all matters of judgment and style, okay? Some people have, but all I was saying is you should have a sense of a horizon on any of these things. Yeah, now, whether if you're impatient after 10 days, probably that seems like a bad idea to me. Impatient after a year, as a student, no, that's a bad idea because you need more. I'm more efficient now because I've been around and done many, many things. So I've learned from past, as you get older, you get more efficient in these sorts of decision making. Yeah, in the beginning, the best way to do that is to try something and fail. Then you'll have learned a real lesson. But you should have a very strong, my view is that as a young person, you should have a very clear, strong sense of achievements, that you want to do by the time you finish your PhD. You shouldn't be happy with one paper, that seems very small. Minimum of 3 good papers, I think that's sort of the lower limit. 5 would be nice. 10 is a bit too much, I think, because unless you're very bright. So I'm saying there should be a seriousness. Every day matters. So that's why I don't like, sometimes we have this meeting. So let's agree to have a meeting to then decide on the other meetings. I don't understand that. For me, I want to get on a project. Nowadays, my view is that if we start something, discuss, a couple months later, we're still discussing, it's time to move on. But I'm at a very different career phase than you are. You have to figure out, look, this is life. You're young. You have to experiment with yourself. You don't know who you are. Experiment with yourself. Change the time scale. Change this. And then you'll start understanding who you are and what you want. But you should have that tremendous sense of urgency where every morning should count to you. The moment you say, yeah, life is infinitely long, you're lost.
Okay, thank you very much on that. And the second question I wanted to ask is, like, you, at the beginning of your talk, you mentioned that you, aside from being a scientist, you also do some, like, in economics, now let's bring some money. Let's do also some engineering because it needs to be efficient. Personally, I was more of the idea of, I want to be very proficient on my field. I study a lot of physics, science, and so, but maybe that made me closed a lot of other, like, paths of maybe a little bit of economics or a little bit of public relations. So how much do you suggest or advise to also get into those other fields to have like a more complete, like, how do you say it, a more complete knowledge so you can benefit your own research?
I think it's very important all of us as human beings and citizens, be very well informed of the world, no matter, even if you're a mathematician, which is a solo research activity, you should. I read the New York Times every day. I subscribe to Atlantic and Economist. I read vociferously, Foreign Affairs. I have a lot of facts in my, when I came a couple of days ago, I was asking how much rainfall happens in this city because I was trying to understand, what is the water capacity. Yeah, this is life. You have to live, you are in this world. You have to be aware of this world. You can't be such a, okay, there are occasional exceptions. Maybe, Dirac was like a loner way and all that. But most of us are ordinary people, okay? So, and we are citizens. We should be very well informed. No excuse if you have a poor sense of geography and, then you're not even living in this planet. It's not a zero-sum game. You can be a broad person and be an excellent researcher. As far as I know, there is no zero-sum game there at all.
Okay, thank you very much.
Are there questions on Zoom? If there are, you can open up your mic and speak. If not, I think one last question.
Yes, here.
Thank you again, Dr. Kulkarni. I think I'm always a student, and I will be a student. Maybe sometime I will finish a PhD, maybe. Why we build instruments if we have tons of data to analyze? Why more instruments and more powerful instruments if we have many?
Yes, it's a very good question. And I've always wondered about that. It's a complex, it's an excellent question. It's a question that the professional societies like the American Astronomical Society or whatever equivalent IAU should be asking, and they will not ask this question. It is against their self-interest to do so. Okay. They are following true statements. An instrument which increases some dimension, angular resolution, sensitivity, wavelength, will teach us something new of the universe. This has always been true. Okay. We are not talking about the Large Hadron Collider because physics is a reduction game. Essentially, they built it, and it turned out that standard model formula in the 60s was amazingly, it's a testament to our, I don't know what it is, some power of mathematics or something that 50 years later, all they did, yeah, we found the Higgs boson, that's about it. Then there's the usual echo chamber stuff. They'll measure this cross-section and that cross-section, none of which amounts to halo beams. It's all consistent, okay? But astronomy is not that way. It is the universe has 10 to the 11 galaxies. Each galaxy is about 10 to the 11 stars. Most stars are in binary or triple systems or more. So the outcomes are infinite practically. Therefore, in our field, if you build a big an instrument with a new capability in any dimension, we will discover. So the reason to build an instrument is obvious. Then the question is how many to build. This is an economic question, okay? And we don't do this sort of economic analysis in science. So let me give one example. And I thought about this a lot, actually. If I say, let's go back to 1975. Joe Taylor and Hulse have discovered a binary pulsar, and the other companion is a neutron star. They see, you apply GR equations, you'll know it'll coalesce. So already we know from GR, okay, what is the signal strength, and from astronomy, we know it exists. Those are the two important things. There is a signal, and in fact, it's not a hypothetical object. It is a real phenomena. So you say, let's go build a gravitational wave interferometer. There were two, then you can say, there's one answer, which is you say, as an SF, what I could say, you should ask the question, how many people and how much money is needed to find the first gravitational wave signal? Okay, this is an industrial formulation. It has to be an industrial thing. This is a very hard measurement. But we don't do that way. So if you ask the question, how many people does it take to change a light bulb, which is the usual puzzle that, then it turns out to be 1, 0, 100,000. So then it turns out the answer is no. We have not thought of this ground up. LIGO started with a small number at MIT and Caltech, and then as they needed more money, they grew. It's easy, it's a sexy subject. Then you get Germany, you get the Italians, and so on. Then you keep growing, because the more people you have, the more money you get. So that is where the self-interest is coming in. So these projects grow for the simple reason funding is directly proportional to the number of people you have. So by the time LIGO made its discovery in 2015, it may have been a very inefficient discovery. That is, we probably had overpopulated the project compared to the minimum necessary to find this. But this is not a result of any industrial planning. Okay, so this will not change. Every country, like time domain astronomy, there literally maybe about a dozen time domain astronomy experiments on, and maybe even more. I can tell you, in most cases, my analysis is most of them are not doing anything worthwhile. Or if it is, it's very minor. But people like to build instruments, okay? And they like to find my own supernova, yeah, so that's, okay?
Okay, I'm afraid we are running out of time, but before thanking Professor Kulkarni, we have one announcement.
Yes, our next speaker is Ryan Foley tomorrow at 4 in this auditorium. So please come so we can continue tomorrow with the discussions, and you can talk with the speakers tomorrow too, right?
Yes,
So
after the talk, they will both have a meeting exclusive with the students in which you can talk to them more informally. So that's all, and let's thank again Professor Kulkarni.